Japan. Please, next presentation.
Thank you.
Professor
Just a moment.
Oh, thank you. Thank you.
Okay. Hello, my name is Tomotaka Kobayashi, and I'm a doctoral student of Waseda University. Today, I'd like to talk about temperature and pressure dependence of anomalous heat generation occurring in hydrogen gas absorption by metal powder. There are backgrounds of this research. It is known that anomalous heat is generated when hydrogen or deuterium gas is absorbed by nickel or palladium powder. There are lots of researches while increasing either initial temperature or pressure in reaction chamber. We developed a small constant volume reaction system in order to validate excess heat generation. This is a photograph of the reaction system. The reaction system enables to conduct experiment while increasing both the pressure and temperature simultaneously. This is because only temperature increase may lead to less reaction due to the possibility that hydrogen gas heated gets out of metal powder such as palladium or nickel. The reaction system is constructed of heater, a reaction chamber, K-type thermocouple, 2 pressure gauges, 2 valves, a gas supply device, and vacuum pump. To prevent breaking down of this system, a safety valve is also installed. The safety valve opens when pressure in the reaction chamber exceeds 1 megapascal. A specification of the reaction system is shown in this table. Volume of the reaction chamber is about 2 milliliter. Ultimate pressure of vacuum pump is 1.6 pascals. Maximum pressure of loading gas is 0.7 megapascals, and maximum temperature of the heater is 300 degrees Celsius. In this report, we conduct fundamental experiment of hydrogen gas absorption. A sample absorbs loaded hydrogen gas after evacuation and preheating. This is a procedure of the experiments. First, sample is set in the reaction chamber. Then the reaction chamber is evacuated by vacuum pump and preheated by the heater. After the preheating, the gas is loaded in the chamber. Temperature changing of the samples is measured by K-type thermocouple. In the experiments, 3.0 gram of nickel powder or palladium nickel zirconium composite powder is used as sample. The experiments are conducted using hydrogen gas and nitrogen gas as the control experiment. The experiments are conducted in the range of loaded gas pressure 0.12 to 0.5 megapascals, and initial temperature of sample 95 to 240 degrees Celsius. This is the result of one of the experiment. In the experiment, the 3.0 gram of nickel powder is used as sample. The loaded gas pressure is 0.5 megapascals, and the initial temperature of the sample is 240 degrees Celsius. The graph on the left shows the result for each gas. The vertical axis means the temperature of the sample, and horizontal axis means the time from the start of the gas loading. According to the graph, there is a difference between the temperature changes in the cases which the hydrogen gas is loaded and nitrogen gas is loaded. And the graph on the right shows the temperature difference between the cases of the hydrogen and nitrogen. The vertical axis means the temperature difference, and horizontal axis means the time from the start of gas loading. According to the graph, about 4 Kelvin of temperature rise is obtained in the experiment using nickel powder and hydrogen gas. In the experiment, temperature rise begins about 400 seconds after hydrogen gas loading. In order to clarify the temperature dependence of temperature rise of the sample, we conducted the experiments with loaded gas pressure of 0.5 megapascals and initial temperature in range of 95 to 240 degrees Celsius. Each of these graphs shows the temperature difference between the cases of hydrogen and nitrogen. The vertical axis represents the temperature difference, and horizontal axis represents the time from the start of gas loading. According to these graphs, about 1 Kelvin of temperature rise is observed at 95 degrees, about 2 Kelvin at 173 degrees, and about 4 Kelvin at 240 degrees. This result may show the temperature rise of nickel powder is affected by initial temperature of the sample. On the other hand, we also conducted the experiments with initial temperature of 240 degrees and loaded gas pressure in range of 0.12 to 0.5 megapascals. Each of these graphs shows the temperature difference between the cases of hydrogen and nitrogen. According to these graphs, about 2 Kelvin of temperature rise is observed at 0.12 megapascals, and about 4 Kelvin at 0.3 megapascals and 0.5 megapascals. This result may show the temperature rise of nickel powder is also affected by loaded gas pressure. Results of the experiments with 0.5 megapascals of loaded gas pressure shows positive correlation between initial temperature and temperature rise of nickel powder, and that of 240 degrees of initial temperature also shows a positive correlation between loaded gas pressure and temperature rise of nickel powder. The graph on the left shows the result of the experiments at 0.5 megapascals. The vertical axis means the temperature rise, and horizontal axis means the initial temperature of the sample. According to the graph, there is a positive correlation between the temperature rise and initial temperature. This can also be said from the fact that a correlation coefficient between them is 0.95. And the graph on the right shows the result of the experiments at 240 degrees Celsius. According to the graph, there is positive correlation between the temperature rise and pressure of loaded gas. This can also be said from the fact that correlation coefficient between them is 0.84. These results may show that temperature rise of the sample is assisted by not only preheating but also gas absorption under higher pressure. And we also conduct the experiments using palladium nickel zirconium composite powder. This is a result of one of the experiments. In the experiment, 3 grams of the palladium nickel zirconium composite powder is used as sample. A loaded gas pressure is 0.5 megapascals, and initial temperature of the sample is 95 degrees Celsius. The graph on the left shows the result for each gas. The vertical axis means the temperature of the sample, and horizontal axis means the time from the start of gas loading. According to the graph, there is a difference between the temperature changes in the cases which the hydrogen gas is loaded and nitrogen gas is loaded. And the graph on the right shows the temperature difference between the cases of hydrogen and nitrogen. The vertical axis represents the temperature rise, and horizontal axis represents the time from the start of gas loading. According to the graph, about 12 Kelvin of temperature rise is obtained in the experiments using palladium nickel zirconium composite powder. In the experiment, temperature rise begins immediately after hydrogen gas loading, and temperature rise sustains about 200 seconds. Now, I've showed the conclusion of this research. We developed a small constant flowing reaction system and conducted the fundamental experiments while increasing both the pressure and temperature simultaneously. As a result, temperature rise of about 4 Kelvin is observed in the experiment conducted for nickel powder about 1,000 seconds after from start of gas loading. In the result of experiments using nickel powder, there are positive correlations between temperature rise and both of loaded gas pressure and initial temperature. This result may show that temperature rise is assisted by not only preheating, but also gas absorption under higher pressure. We also conduct the experiments using palladium nickel zirconium composite powder. About 12 Kelvin of temperature increase is observed in the experiments until 200 seconds after from start of gas loading. And here is the outlook. We will conduct more experiments to clarify the temperature and pressure dependence of temperature rise of the sample in the experiment using a palladium nickel zirconium composite. This will also be important as basic database for the focusing compression engine proposed by us. We are developing the new prototype of the focusing compression engine. In the near future, we will conduct cold fusion experiment using it. This is the end of the presentation. Thank you for your attention.
Thank you for your good presentation. Please, any questions? Zachary, please switch on your microphone.
Yes, thank you very much for this very interesting presentation. You know, I have a question. You are using a small reaction chamber, you know, you put the nickel inside and hydrogen inside, and this reaction chamber is heated from outside. There is always a small risk that hydrogen diffuses through the wall of this reaction chamber. So in this heater volume, you can get in this gas not more air, but a small amount of hydrogen mixed with the air, so that it changes, it may very well change the thermal conductivity of the gas between the heater and the external wall of this reaction chamber. If you see, and of course, the amount of hydrogen in this heater internal volume increases with the leak of hydrogen through this reaction chamber wall, and this leak may increase with the temperature and the gas pressure inside this reaction chamber. Did you evaluate if there is any effect like this change of, like this leakage of hydrogen through, by diffusion through this reaction chamber, through the wall of this chamber?
Did you ask about the leakage of the heat from the heater?
No, I am asking about leakage of hydrogen out of this reaction chamber
Hydrogen.
into the heater.
Okay, we conducted the snoop test before the experiment, and it's okay not to make leakage. The reaction system or reaction chamber can keep the whole hydrogen gas in itself.
Okay. What is the thickness of this the wall of this reaction chamber?
Thickness about 1 millimeter of the reaction chamber wall of